Okay, in class when we introduce a new idea called trigonometric ratios, I generally will do a little discovery. So this video is going to walk through that discovery. Hopefully it makes sense where I'm just doing it on this screen. And I'm just going to walk through these steps. You're welcome to walk through the steps as well on your paper in your guided notes book. So first of all, this says below you're going to create two right triangles. Now, one of our goals today is to look at trigonometric ratios as just ratios, right, on parts of a triangle. So triangles have three different sides. When we talk about a right triangle, they have that hypotenuse. They have two acute angles. So over here on the right, I'm going to label, here's one acute angle down there at the bottom. The other one is at the top, and then they have the right angle. So we're looking kind of at our acute angles today, and we're going to look at how the ratios relate to them. If you think about the angles and as they grow, if this is a really tall triangle, right, and this angle here obviously is going to be a different angle than the one up here. This one got much smaller, that top angle in the triangle, and notice when it got smaller, the side length over here got smaller. Just because of the nature of the triangle when you change those angles. It still has a hypotenuse, but those legs are changing lengths. So our trig ratios is going to talk about, well, how does this angle, how does it affect that length? And how does this angle changing, how does it affect this length? What's that relationship? How does that affect the hypotenuse? So when we look at this, below you're going to create two right triangles, and we're going to show how the angles create similar triangles. And so these ratios can be consistent. So first of all, we're going to measure the length of a base leg. Now you get to choose how many centimeters you want it to be. So I did this specifically already, and I am going to use the length measures that I made. So let's say I take my ruler and I measure the bottom here, and I measure out, let's say 4 centimeters. Okay, that's what I did earlier. And it wants us to then create a 30-degree angle as one of the acute angles of the triangle. So we already have our right angle here. Now we're going to create a triangle here, and we want this angle to be 30 degrees. So if you're measuring an angle, you use a protractor. And I have a picture of a protractor right here. And essentially what you do is you move this protractor. I don't know that it's going to let me move it anymore. Let's see if I insert another picture. Oh, there we go. Let's see if we can make it a little smaller. So let's say I take this protractor, and if you put the center of the protractor, now you can't see it, but right on the dot, and I line up my protractor, then it allows me to take this, and this might be super weird over this image, I've never tried it, but let's say that's my dot right there, and this was my 4 centimeter side. Now I probably made it longer or shorter. But when I do that, when I make a 30-degree angle, you'll notice here on the protractor, there's my 30 degrees. So if I draw from this dot and I extend this line through that 30 degrees, and that's my other vertice, this has now created my triangle where this angle must be 30 degrees because we measured it with that protractor. So when I do that, and I'm going to see if I can draw a line here through the 30 degrees. We're going to go through 30 degrees and stop right there. Yep, pretty close. That's the hard thing about doing these by hand, actually. You'll see my ratios are close but not perfect. So there's my triangle. Now if I go ahead and measure, so number 3 down here, if you're looking at these, number 3 asks you to carefully measure and label the 3 sides of the triangle. So again, I measured mine earlier, and this ended up being 2.25 centimeters when I measured it. And my hypotenuse here ended up being 4.55 centimeters. So this was just me using a ruler. It asks us in step 3 to label the 30-degree angle as A, the other one is B, and the right angle as C. And we could do the same thing again. I'm just going to show you again one more time. Let's say I choose this top part to be, well, let's say I measure on this side. Let's do this side. So let's say we do this side, and we decide instead to do like 5 centimeters. So again, if you lay your protractor on there where this is at that 0, I'd have to rotate my protractor, and then I create, say, a 30-degree angle. Now again, when you freehand it, I probably didn't create a 30-degree angle, so that's why it's important we use our protractor. But I'm just going to call that 30 right now and use the measurements that I got. So this was 2.8 centimeters. There's my 30-degree angle as the A, and there's my B. So here I have two triangles. Now again, notice these are similar triangles because they both have a 30-degree angle. They're just rotated in different ways, right? Because that 30-degree angle is the same, the 90-degree angle is the same. These are similar triangles, which means the ratio of the sides should be the same length. So I'm going to zoom out just a little bit so I can keep my triangles on here. This says now number 4. Now use the measurements of your sides to find the following ratios, write them both as fractions or decimals. So the first one asks us to look at BC and put it over AB. Well, B to C in my first triangle is this length right here, so that would be 2.25, and I'm going to put it over the length AB. Now AB is this hypotenuse length here, so 4.55. So my ratio here is going to look like 2.25 over 4.55. If I put that into my calculator, 2.25 divided by 4.45, I end up with 0.4945. If I do the same thing for triangle 2, so here's triangle 2 information, B to C, again, I look up here, B to C is this little short leg, over A to B, which is this hypotenuse. So I'm still using those same two types of legs. That's 2.8 over 5.8, which in this case ends up being about 0.4828. Okay, then we do the same thing just with other sides of the triangle. So ratio A to C, so if I look at my triangle 1, I'm taking A to C, which is 4 centimeters, and putting over A to B, which was 4.55. So this is 4 over 4.55, which again, if we put in the calculator, is about 0.8791. If we do the same thing with the next triangle, A to C is here, 5 over 5.8. which is approximately 0.8621. And then your last ones, again, these use both of the legs. You'll notice this bottom one, if I look at B to C here, it doesn't use the hypotenuse, it's over the other leg. So you're looking at 2.25 over 4. Oh, that's a 4, which is approximately 0.5625. And in the second triangle, you have 2.8 over 5. 0.56. You'll notice that these decimals, if you look at this, are a little bit off, right? My measurements are not perfect, but you'll also notice that each of these values are very close. And the more we do of these and we take the average of the ratios that we find in the class, we end up getting very, very close ratios as we work through all of these. Now the cool thing is the trig ratios, each one of them relate two of the sides of the triangles. So again, if I was looking at this 30-degree angle, and that's kind of the one I was using, we call it reference angle, then there's three sides of the triangle. There's this hypotenuse, and I'm just going to label it, right? This is my hypotenuse. There's this leg over here, and we call this the opposite leg because it's opposite of the 30-degree angle that I was talking about. And then you have the leg next to the 30-degree angle, and we call this the adjacent leg. So there's three legs. The hypotenuse is always the one across from the 90-degree angles, right? You have your hypotenuse across from that. You have your opposite leg, which if I'm using this 30-degree angle, then that one's the opposite leg, and then you have your adjacent leg. Again, if I'm using angle A here, notice the opposite leg in this second triangle is the 2.8, so that's my opposite leg, and the adjacent leg would be that 5 there. Now if you switch and use angle B, notice your opposite leg becomes this one, so that adjacent leg and opposite leg would switch, your hypotenuse never switches. So down here, if I was listing this out, notice BC is like that opposite leg over that hypotenuse is AB. So this we could say was like the opposite leg over the hypotenuse. The next one was the adjacent leg over that hypotenuse. And then on the bottom one we did BC. So again it's opposite but over AC. So those are your two legs. So this is the opposite leg over the adjacent leg. So notice each of these ratios are using two different parts of the three legs of the triangle. And We gave these trig ratios names because you'll notice that for any triangle with a 30-degree angle, these are going to be very, very similar, right? These ratios will be consistent between all of them. Now, we obviously don't memorize it, but our calculator does, so it's very helpful. This first one we call a sine ratio, okay? Sine is spelled S-I-N-E. This next one that relates to the adjacent leg we call a cosine ratio. And the last one that relates the two legs we call the tangent ratio. These are the three ratios, and you'll notice, I'm going to show you this really quickly, is if I wanted to look at the sine of 30 degrees, this is the way we write it. We always write the sine of some angle measure. Sine of 30 degrees, I would go to my calculator. I'm going to show this really quick, and in the next video I'll actually explain the calculator part. But if you go to your calculator and you push that sine button that you've always wondered what it does right there in the middle, and I accidentally put a 7, whoops. If I do the sine of 30, I end up with 0.5. If you look back at our diagram, I'm going to write 0.5 here. You'll notice that these ones were super close to 0.5. So the opposite leg is always, right, related to the hypotenuse in that it's going to be the sine of 30 degrees will be 0.5. We could do the same thing for the other. So this time, if I take the cosine of 30 degrees, the cosine is about 0.8660. So cosine of 30 degrees, about 0.8660. So again, you'll notice that that's very close on those two. And then lastly is the tangent. So if I do the tangent of 30 degrees, I end up with 0.5773, or 4 if we were rounding. So the tangent of 30 degrees is equal to 0.557. Let's say we round that to 4. So again, my values are not exact because drawing is really challenging. But the cool thing is anytime I take the sine of 30 degrees, I know that it's going to be 0.5. So if I ever, let's say I had a triangle and I didn't know what the degree measure was, if the opposite leg is related to the hypotenuse by 1/2, and that's the ratio, then I know that this is a 30-degree angle. If I know this is a 30-degree angle and this right here is 6, then I know the hypotenuse has to be 12, right? Because this has to be a ratio of 1/2. So we can use these ratios to help us identify parts of a triangle, and specifically these triangles are going to help us determine different lengths and heights and measurements of objects. Lastly, this question says, can it be assumed this pattern of ratios will hold for every right triangle? Now again, right triangles are key here that we're going to use that has a 30-degree angle. The answer is yes. We would say yes, okay, because all right triangles that have 90, 30, 60 degrees will be similar triangles, right? So the triangle legs will maintain the same proportional relationship. So we just want to make sure that we kind of understand that, okay? Again, trig ratios, what are they? Sine, cosine, tangent, and all they do is relate different sides of the triangle together. So in the next video, we'll talk about using those trigonometric ratios to find